Today I would like to start talking about objects like they really are. Yeah, because so far we approximated object by a particle. And well, what is convenient about thinking about an object as a particle, then if we want to figure out where that particle is, we need only three numbers. Now, in order to say where I am, if you really think about me as an object, three numbers won't be the same. I mean, won't be enough. Yeah, because for example, if I do something like this, do you see that I change my position? The space which I occupy now is different than when I had my hand like that. Three numbers now will not be sufficient to describe my position. I am not a particle, but I am a system of particles. So in principle, if you divide me into a particle, for each particle you can assign three numbers, identifying that position, and now when you identify position of all my particles, then you will know where I am. So how many numbers do I need? A lot, right? More precisely, I mean, if I did it like that, so this is the most general, because I am not actually that complicated object, so we can reduce the number, that number, but in principle, for an arbitrary object which can change its shape in an arbitrary way, we will have 3 times the number of particles, numbers, to describe position of this object. Well, we will start with an analysis of an object which can take an arbitrary shape. So we can think that an object is a system of particles, which each of them can move in principle independently. Well, if we have a system of particles, then we can now generalize the quantities which describe motion of those particles by adding just one adjective, total. So for a certain system, for a certain physical quantity, which is defined for a single particle, we define the same quantity for the entire system, and we call it then total value of that quantity by adding the values of the quantity for all particles. So for example, what do we understand by total mass of a body? Think about total mass of your body. What is it? You have to add masses of all particles constituting your body, and then you will get total mass of your body. Well, let's think about total momentum of your total momentum. It is that we will have to add momenta of all particles constituting your body. That way we will get total momentum. And to make a distinction between a quantity for a single particle and for a body, we use capital letters consistently with the book. So total mass, for a total mass of an object, if we think about an object as an object, not as a particle, and in principle we should put capital M. Total momentum of a system will be capital P. Sometimes there is a problem, because like for total kinetic energy, we already, for a single particle, we use capital K, so that we don't confuse this K with another K, and we actually have two more small K's. One is called Boltzmann constant, and another one is called Coulomb's constant. Those we will learn about those in the future. So we don't traditionally use small k for kinetic energy of a particle. So it can lead to a kind of confusion. If you are confused, you can always add every time a subscript, TOT, for example, or total. All right. Now, the quantity which we discussed last time, total momentum, momentum, we defined so far momentum of a particle. For an object, what do we understand by total momentum? Sum of momenta of all of the particles. Now, similarly to this, what happens with energy, appropriate energy, because not every energy is conserved, we have to know when what energy is conserved. Also, if we think about momentum, under certain circumstances, total momentum is also conserved. Now, there is a big difference between conservation of energy, which we discussed so far, and conservation of momentum, which we are going to discuss today. Yeah, because so far, when we discuss conservation of energy, I think, recall examples of, when energy, when and which energy was conserved. So let's say that when kinetic energy of a particle was conserved. Under what circumstances, how that object had to interact with the rest of the universe so that its kinetic energy was conserved. You have just to look at the work energy theorem. According to work energy theorem, how it had to interact with the universe so that its kinetic energy was not affected. What the work energy, what the first version of work energy theorem says, that work is equal. Well, we have a first version of it. Work is equal to kinetic energy. Which work? And this is incorrect. We have to change something. It's the formula says delta K equals delta W. Now, explain it to me. So change in kinetic energy, again, make sure do not confuse change in a quantity with a quantity. Don't confuse change of the balance on your checking account with your balance, right? They happen to be equal only if the initial balance was 0. So change in kinetic energy is equal now, what is delta W? Work over the same interval, not change in work. We don't have instantaneous value of work, therefore we don't have change in work. So delta only indicates that it is in the same time interval. All right, so if kinetic energy is conserved, what is the change in kinetic energy? 0, which means that how the object had to interact with the universe in order to have 0 change in kinetic energy. Okay, right. The universe could not perform work on that object. Now, it doesn't mean necessarily that the object did not move, because we can have a situation that object moves and work is still 0. If we think about a satellite moving in a circular orbit around the Earth, what is the work done by the Earth on that, which is the only one which we could consider now, because the satellite, the only significant force is exerted by the Earth. So how much work does the Earth perform on the satellite moving in a circular motion? 0, because how come that it's 0? Indeed, it is 0. The satellite is going to move with a constant kinetic energy, therefore. How come that work is 0? Force is exerted and there is a displacement. No, displacement is not 0 of a satellite moving along a circle. It is accelerating. Satellite is accelerating. You have forgotten actually what the satellite does. Let's review it again and see why kinetic energy is not changing. As I hear us say, the Earth and the satellite is flying like that. Let me actually give again a trap which I already told you once. So how much work is done along a closed loop? Why? Because what? Because it came back because the displacement is 0? Actually, you could use this argument over here, but you will have to justify it. How come that you can use the fact that in in a complete loop, work was 0. Because gravity is conservative interaction, correct. So work is opposite to change in potential energy, and potential energy is a function of position. So if object returned to the original position, then work definitely has to be 0. However, if you think about how much work did the whiteboard do on the pen when I was drawing it, tell me, positive, negative, or 0? Consult with each other. I asked you already once this question. We discussed. Who said negative? You remember it or you see it? Yeah, okay. Work is negative. And Josh remembers it. I don't want, this is not good answer. You cannot be an engineer because you remembered something. Because then if you forget, you are in trouble. Not mentioning, then maybe you remember it wrong. It has to be crystal clear that it's 0. Consult with each other. Why is it 0? Negative, sorry. Why is it negative? And let me remind you, think about how much work was done if the pen moved from this location to this location, and then from this location to this location. We have to divide the path into small pieces and consider work done along each of those pieces, differential pieces. Did you get it? Okay. Yeah, look that along, this is correct answer. JD said that if you move from here to here along a differential path, then, well, displacement is in this direction, frictional force was in the opposite direction. So scalar product of the force and the differential displacement was negative. We got a negative number. And we can, JD says that, can recognize that along all of those differential fragments, this was the case. So work was negative. How come actually that the total now doesn't work? For gravity it could work, and for this one doesn't work. For friction doesn't work. Because friction is not a conservative interaction, correct. But now, well, if we want to use, to figure out how the speed is affected from this location to this location. Now, is kinetic energy of the satellite conserved or not? Consult with each other for, let's say, 15 seconds, and then let's vote. Well, so who believes that kinetic energy is conserved? Who believes that it is not conserved? Who has no opinion? What the rest do actually? Somebody who said that it's not conserved. What is your argument? Because we have that change in kinetic energy is equal to net work. Right? So, what's your argument? We say? Well, no, this is now the path. So what? That it didn't complete. Oh, so you say that potential energy here is different than potential energy over there, right? This is, Mark, what you wanted to say? No, I mean, this is good approach. This is good approach because now it isn't wrong, it is a mistake. Because if we compare potential energy at this location and potential energy at this location, I mean, recall that potential energy is gravitational constant, mass of the first object, mass of the second object, divided by distance from the center, minus in front of that. So gravitational constant in both situations has the same value. Mass of the Earth and mass of the satellite didn't change. Now, position changed, but the distance from the center did not change if the orbit is circular. If the orbit is elliptical, like it is, then indeed it does change. So, for example, we as the Earth, we run faster in the winter than in the summer, our summer, because we are further away from the sun in the summer than in the winter. Well, so I buy this argument because Mark could think that since gravitational work was done, then this number here is a positive number, or well, non-zero number. It means that kinetic energy changed. However, this number is zero. Well, we see over here that way. We can also take a look now. How come that? Can we see that work is zero without using concept of potential energy? Because indeed, if we use concept of potential energy, which is a very good approach, because it's easy to calculate work due to conservative work, to conservative interaction when I mean. Just by comparing potential energy at these two locations. Now, what direction is the force over here? Toward the Earth, right? The gravitational force is toward the Earth. Right? Displacement is along the path. What's the angle between the displacement and the force? 90 degrees. All right. So, if I calculate work, I will have to multiply magnitude of the gravitational force times magnitude of the displacement times cosine of 90 degrees. How much is cosine of 90 degrees? Zero. So product is zero, which means that along this path work is zero, and along each of those paths work is zero. So kinetic energy in this situation is conserved. Now, on the quiz yesterday, actually, I was very upset with your answers, and I know that it is kind of a pitfall. I mean, this misconception. I want you now, because it is that we have to know under what circumstances what energy of what is conserved. In general, when we use word energy, it's not conserved. Neither specific energy is not conserved in most cases. Yeah, think about when you walk through the day. Do you maintain your kinetic energy? No, right? Because right now your kinetic energy is almost zero, unless that you make some kind of you move a little bit. Well, in order to get to your car, you have to change kinetic energy, because with the zero kinetic energy, you will never get there, right? You need to gain kinetic energy for a moment to get over there. Now, when you get to the car, you have to get rid of it, right? Conservation of energy does not say that your kinetic energy is conserved. It says that now, in order to get rid of this energy, you have to give it to something or somebody. Now, how about your gravitational potential energy? Is that one conserved as you walk to the car? Do you? Where did you park your car? In the parking garage. Is it on the same floor as this one, on the same level as this floor? No. Yeah, you won't. If you go over there, you will have to change. You will have to change gravitational potential energy, because otherwise you will have to be all the time on the same level. Yes, okay. For example, I can walk over there and without changing potential energy. So my potential energy now was conserved. However, if I go over here, but my potential energy already is not conserved. All right. So you have to always remember what of what, and what energy of what, and under what circumstances. And in general, energy is not conserved. Repeat it to yourself. Correct. Now consult with each other. How is it consistent with the conservation of energy? Why I'm asking you to say that energy is not conserved, and at the same time I'm telling you that energy is conserved. Yeah, you have to recognize what energy of what and when. Well, I made a really wide digression. I'm a long digression, but if we think about conservation of energy, which we discussed, so what did we discuss? First of all, that, well, indeed the total energy is not conserved, although we never really specified that. We said that it has to go to somewhere else. But let's say that when mechanical energy is conserved, it's also from work energy theorem. So kinetic energy, we can see that kinetic energy is conserved when the object does not interact with anything else. Mechanical energy is conserved when this work is zero. What's that? Non-conservative work, correct. A work which we haven't included in the conservative interaction. So, for example, well, if I toss this object over here and ignore that it interacts with air, so if I think that it only interacts with Earth, and gravitational interaction is conservative, so we have gravitational potential energy. This object has gravitational potential energy, and if I add gravitational potential energy and kinetic energy of this object, since there is no other work done on it, that sum is going to be conserved, right? But it's kinetic energy, mechanical energy of the pen, right? So it was always energy associated with a single object. Now, in case of conservation of momentum, momentum is also not conserved. Momentum of an individual object is not conserved. The total momentum is conserved. This is what the conservation of momentum says. If I have a system of particles which does not interact with the surrounding, it only interacts with itself, then total momentum of that system is constant. Let's take a look why. I want your help to justify each step. So I wrote here the expression for the rate of change in momentum. If it is constant, what should I get? What should be the result? Zero, correct. What's zero? Zero vector, correct, because if we calculate the derivative of a vector valued function, we should get a vector function. All right, well, I wrote that. Where did I get this from? Help me. Yes, Mark? I added momenta of individual particles in order to get total momentum. Why? Because this is how we define total value of momentum. All right. How did I get this thing? This step. Now, this is not a physical step, it's a mathematical. So justification comes from math. What is it? Derivative of the sum of functions is equal to the sum of derivatives, correct. Where did I get that from? And what does it really mean here? Correct. For a particle, net force. Yeah, so here I have derivative of momentum of ith particle. Yeah, so think about that I is number 3, I'm watching particle number 3. If I is 7, I'm watching particle number 7. Now, so the net force on the third particle on this or on the seventh particle is equal to the rate of change in momentum of that particle. Now I wrote it that way. What did I do over here? Well, because now here this is net force on ith particle. Let's think about that. In the system we have 5 particles, right? So what exerts force on the first particle if the system is isolated? The remaining 4 particles, right? So if I plug in for I number 1, then I should start with 2, 3, 4, 5 to identify forces exerted on particle 1. Now, in order to find out force exerted on particle 2, I will have to add forces exerted by particle 1, 3, 4, and 5. Now, for particle 3, I have to calculate, to add forces exerted by particle 1, 2, 4, and 5. Do you understand that? All right. So actually, I have now to calculate through all possible indices between 1 and 5, excluding situations when indices are identical. Correct? Now, it means that now if I have a combination of indices 1, 3, I will have also a combination 3, 1, right? Because it can be that I is 1 and j is 3, and then when I continue, I will find a situation in which I is 3 and j is 1. So that sum actually contains all possible combinations. Now, addition of vectors is commutative and associative, so I can regroup the terms. What will happen if I bring force 1, 3 and 3, 1 and associate them? They will add up to 0. Convince me.
The cosine of the angle will change between the two and they'll offset each other.
This is not scalar product. Don't mess up with the cosine of 180 degrees. Give me a better argument why they are opposite. Yes, Andrew. Newton's third law says that, right? Now, is there actually a combination that of numbers I, j among 1 to 5 that it doesn't have a couple? No. All of them, we always can group them, so we will get a number of zeros. If we add all of them, what are we going to get? 0. So the sum is 0. What does it mean then? What is constant?
The momentum of the first system.
No, it's not momentum of the total system. Yeah, what did you say?
Particle?
No. Total momentum of the system. Repeat it again. What is conserved then? Total momentum of the system, right. Well, I want now to use it to certain type of interactions which we refer to as collisions. And collisions are interactions which happen over a finite period of time. We think about it that collisions are happen over a short period of time, although as I said, in case of galaxies, here you have a picture of a collision of 2 galaxies. They can collide over several millions of years. Now, collisions, actually, how about if you like take a look at the last thing. Collisions are so strong interactions. In collisions, the interaction, that brief interaction is so strong that even if external interaction on the system exists, its effect is insufficient. I mean, it's, negligible. The effect of external interaction is small. So, although this is approximation, we can ignore external interaction if we have this intense interaction of a colliding body. So, for example, if two cars collide in an accident, if an accident happens, the two cars push each other so strong that you can forget that there is a normal force, that there is gravitational force, and that there is a frictional force with the road. In the collision, these don't matter. What matters is really how the two cars interact. So, because in a collision, we can always consider that interaction is always internal, so the total momentum of the system does not change. Now, depending on this, what happens with the total energy, we have entire spectrum of collisions, and the most, I mean, on the ends we have a collision which we refer to as inelastic collision, and in an inelastic collision we have maximum loss of total kinetic energy, and we can also have elastic collision in which the total kinetic energy is conserved. So in elastic collision, total kinetic energy is conserved. In a non-elastic collision, we have maximum loss. It doesn't say necessarily that we have to lose all of kinetic energy, although there are situations that entire kinetic energy is lost in the collision. All right. Now, so in a collision, we can actually predict how the motion is going to be affected. Now, what quantities do we have which describe motion, which are related to momentum? Well, momentum itself is a quantity which describes motion, but usually we will be interested in velocities. Although momenta are as good, I mean, so in principle, I could write down this as and say it in terms of momentum. So in a perfectly inelastic collision, and actually in any collision, total momentum is conserved. So momentum of the this is for two particles. So if I take momentum of the first particle and add to momentum of the second particle before the collision, after the collision, the total momentum is the same. And what happens in perfectly inelastic collision is that either before or after the collisions, the particles have to stick together, to be glued. So perfectly inelastic, oh, here is a perfectly elastic collision between my hands. They collided, and afterwards, I could do it actually like that too. This was also inelastic collision. After the collision, the two objects move with the same velocity. Now, also, this was an elastic collision. So my fingers pushed against each other, because at the beginning velocities were the same. Both palms didn't move. Now they interacted, and so before we had the same velocities of all colliding elements. Well, find that momentum has to be conserved. It relates final velocity with initial velocity of the two particles. So we can find out that final velocity is dependent on initial velocities in such a way. I mean, this is a collision actually in which initial velocities were different and final velocity is the same. You could write down similar equation for the other situation. In a perfectly elastic collision, we will have two equations now. Total momentum is conserved because it is conserved in all situations. However, this time we have two velocities after the collision, and additionally we have total kinetic energy must be conserved. So here I have kinetic energy of the first particle plus kinetic energy of the second particle. Both are before collision. And here's kinetic energy of the first particle and kinetic energy of the second particle after the collision. And actually, I want now to show you a certain interesting example I mean, I think that it is, I mean, it's simple, but I think it was something which was very cool, which we did over the last 50 years. I'm talking about space travel, actually, and how we use collisions in space travel. If I want you to go to analyze how to get those, really, for a simple case, the head-on collision. So let's say that it means that initial velocities are along the same line and final velocities are along the same line. So we can find out what will be the value of velocities of the two colliding objects after the collision if we knew velocities before the collision. And actually I want to analyze a situation in which one of the particles is very heavy and one of the particles is light. Something like, for example, if I think about one particle is Jupiter and another particle is our spacecraft, and we send our spacecraft towards Jupiter and ask it to bounce off from Jupiter. How it is going to move? So let's think that M1 is object 1 is Jupiter, object 2 is the spacecraft, which means that M1 is huge compared to M2. So how much will be, let's see how the collision will affect motion of Jupiter in such a situation. We know it, right? How? It shouldn't, right? It shouldn't. Well, let's take a look at this formula if we get it. So final velocity of Jupiter after the collision with the spacecraft. M1 is much greater than M2. How much is then this quotient? 1, right? Because this is a huge number, this is a huge number. That quotient is practically 1. So this term is 1. How about this term? 0. M2 is much smaller than M1, right? So this is 0. So we get that final velocity of Jupiter is equal to initial velocity of Jupiter. Do you see that? Now let's take a look at what happens with the spacecraft. So final velocity of the spacecraft. Let's start with this term. What happens with this term? This is initial velocity of the spacecraft, and this term now, M1 is much greater than M2. So what is that quotient? 1, right? So we have minus 1, which means that the spacecraft, that this term changes the direction, right? So if it was traveling this way, now it flips and travels the other way. However, final velocity requires addition of this term. Now, how big is this term? It's not 0 this time. Not 1, 2. Correct? We have 2m, and this is practically m. So this is 2m, right? So final velocity of the spacecraft is now going to be equal 2 times initial velocity of Jupiter plus, well, inverse of that initial velocity, right? Do you see that? Well, we use this trick. I mean, it was not exactly head-on collision, but we are using it. We are using it to travel in space. Yeah, because the rocket engines are pretty weak. We don't have powerful. We haven't developed yet warp drive, and the drives which we have are really weak. We cannot speed up those objects to really fast. So this is what we did. Oh, well, I mean, on screen it looks much better. How about if I turn off the lights completely? So This is the time when we launched the spacecraft. Well, it flew, interacted with Venus for a brief period of time. So it collided with Venus. Now, it collided gravitationally. This is referred to as gravitational swing shot. Oops. So then it briefly interacted with Venus, traveled further, and bounced off again of the Earth, interacted with Earth at this point over here. Interacted again with Venus, then over here interacted with Jupiter, bounced off Jupiter, and reached Saturn. Now all of this trip still was 7 years, yeah, because it was launched in 1997, then reached Jupiter in 2004. But we designed this process in such a way that the propulsion was mainly from bouncing off from the planets. Now I hope that this works actually. Yes. I have a simulation of a collision. So here is Jupiter, and actually I put 3 Cassinis over here. Yeah, this is probe and this is probe, and well, when I turn on this, at particular intervals, it says how far the spacecrafts move. Now, see what will happen when it gets closer and closer to Jupiter. It starts interacting. The first one interacted, and this is what will happen after the collision. Yeah, so over here, it was accelerated by the gravitational field of Jupiter. Now it swung behind. Yeah, so Jupiter actually caught it momentarily on kind of an orbit and pulled it back and then tossed forward with much higher speed than before. Okay, now let's go for the next slide, and this one might be useful in a bar. You have such a puzzle. At what? Well, let's start with this. Well, you are about to win the game. In which pocket are you going to sink the ball? If you are an advanced player, actually you can do it. I mean, 2 ways. Who is a good pool player? JD, you are? Oh, you are? Yeah, so for which one would you aim?
The bottom left.
The bottom left. Now, a beginner like me would obviously aim for this one. Right? Josh, what's wrong with this one? You are going to scratch the white ball. Right? Now, it comes from the fact that, well, if you hit it this way, yeah, because in this way you can recognize that this ball will bounce toward that pocket, right? But now, conservation of momentum. The balls have the same mass, so conservation of momentum relates velocities this way. Collisions are elastic on the billiard board, so kinetic energy is also conserved. Now, if I now substitute this expression over here, oh, by the way, masses are equal, so I can cancel out, and now I can substitute this sum over here. So I will get this expression, and if I eliminate similar terms on both sides, I will make a conclusion that the scalar product of final velocities has to be 0. What does it mean? When scalar product of two velocities, velocities of the ball after they bounce off each other is 0. What can you say about the two velocities? Well, it can happen that one of the velocities is 0. So if you hit straight, one ball will stop and the second will continue. But over here, they both will have non-zero speed, which means that how is it possible that none of the velocities is 0 and the scalar product is 0? The angle is 90 degrees, which means that you are going to sink both balls. All right, this is all for today. Thank you very much.